We're going to start talking about the relation between two continuous random variables. Before we do that, let's see what happens when we just have one. If we just have one random variable x that has density f of x, then we can draw the density because the values of x, these are in one dimension. They're all along the line. But my screen has two dimensions, so it allows me to plot the density. You see this curve here. And I can also draw probabilities as areas under the density curve. This is familiar to us. When we lift up to two dimensions, however, and now you're looking at x and y, which is best to think of as a random point, xy, then the possible values are themselves the entire plane. And so your random point could be anywhere. And the possible values are two-dimensional. So now if you think about the probability density, it's no longer a curve, it's a surface over the plane. So I think the best thing for you to imagine is that the possible values are your table, and the probabilities are represented, or the density is represented by a kind of wavy sheet over your table. The probability density is now a surface over the plane. Instead of this curve that we have here. And probabilities are volumes under the surface. So the one-dimensional possible values that are the line became the two-dimensional possible values that are the plane. The density curve became a surface, which I can't draw because it is coming out of my screen at me. And probabilities that were areas have now become volumes. Now all of this has to be made formal, and we have to be able to execute. We've got to be able to find these probabilities. But before we do that, let's take a look at a few joint density surfaces. Here's one. This is a classic. The density stretches, the possible values are the entire plane, and x is centered at 0, and y is also centered at 0. And you have the classic bell-shaped, bell-shaped distribution. This is called jointly normal variables, which we'll have a lot to say about. For now, just keep in mind that we can't easily by hand draw pictures like this. So we will invariably only draw the possible values. You have to imagine the surface over the possible values. And so if I think of the possible values, there's my plane, and that is the origin, and this bell is centered at the origin. And you see it's very high near the origin and tapering off. And so the thing to do here is to imagine simulating values of the random pair xy. And the simulation, because of where the density is high, you're going to get a lot of points near the center, and then getting rarer outside. And later we'll talk about this particular density having a circular symmetry, which is why you see me drawing those what looks like concentric circles. But the point is, the higher the density, when you simulate, the more crowded you expect the points to be over there. Here's another. Here now the possible values of x, that's 0, 0. And so the possible values of x are the positive quadrant. The possible values of xy are the positive quadrant. So you have both random variables are positive, and you can see this density is very high near 0, 0, so you should expect a lot of action around here if you simulate, and then less as you go out. And here is a third. This one is on, what if I look at the points x comma y, then x, values of x are from 0 to 1, but look, it's flat. There's no density. I mean, the density is 0 in some regions, and the values of y also from 0 to 1. And so it seems to me that the action is on the unit square, actually not even on the unit square, it's on the upper triangle. So x has values 0 to 1, and y also has values 0 to 1, but the density is entirely on this upper triangle. It looks to me there's like a lot of action here, and then maybe tapering off. And notice that you can tell all this without knowing the equations of any of these surfaces. You can just tell by looking at the heights. And there is something you can tell with this third one that's quite interesting, which is that you can see by where the density is positive that y is always bigger than x. There's no density and hence no probability elsewhere. And so if y is always bigger than x, you can conclude immediately that x and y are not independent. You don't need to know what the density surface is in this case. You can just tell the lack of independence from the possible values. If knowing where x is tells you something about y, so if I knew that x was somewhere between, say, 1/3 and 2/3, then I know that y cannot be below 1/3. So knowing something about x tells me something about y. Immediately I have a lack of independence. I have dependence instead. In the top two figures, the possible values are rectangles. One is the entire plane, one is the positive quadrant, and you can't tell just by looking whether they're independent or not. There's a little calculation that has to be done, and we'll see that later. But if the possible values are not a rectangle, you know immediately that you do not have independence. So that much we can tell just by staring at the surface. And now let's start actually writing down what formally what a density might be. And so a function f now of two variables is a joint density if it defines one of these surfaces. So first it's non-negative. And second, the total volume under the surface is 1. And so I'll write that in English. Total volume is 1, and the volume under the surface is a double integral just as the area under a curve is a single integral. And here we are integrating over all x and all y. So that's the total volume under the surface, and that better be 1. That makes your function f a joint density. And it is the joint density of random variables x and y if probabilities for x and y are volumes under the surface f. And so let me just draw the possible values again. Here are the possible values, and supposing here is some region A, and remember I'm throwing some random point down. So if I look at the probability that my point falls in my region A, then that probability should be the volume under the surface F over the region A. And so you have to use your imagination now. Above the plane and above A, there is your wavy sheet surface, and you have to imagine the volume under it. Formally, mathematically, that is the integral of the function f, that is the integral of the surface, over the region A. And we're going to spend quite some time with specific regions and trying to figure out exactly what is the calculus that makes us integrate, that helps us integrate that and come out with a number. But for now, the key is to remember that probabilities are volumes under surfaces, and the technical issue, the calculus issue, is how do I work out the volume. But the probability just says that the probabilities are volumes. There is one very interesting and useful volume that you can find without doing any calculus whatsoever. And that is when you look for the probability that x and y are the same. So if x and y have a joint density and you look at the probability that x and y are the same, well, then you better identify the region whose probability you're trying to find. That's all possible values, that's the plane. And let me see if I can use a different color. Now, x equals y, what region is that? Well, that's the x equal y line. It's kind of 45 degrees, not quite. My region is the x equals y line. And so my probability is going to be the volume under the surface over this line. Now, what's the volume over any line? Well, lines don't have widths. The width of a line is 0. And therefore, this volume is going to be 0. This is the two-dimensional analog of what we saw in one dimension, which is that if you have a random variable x that has a density, then the chance that it's equal to any particular number little x is 0, because that's the area of a line, and that area is 0, and here you have the volume over a line, and that volume is 0. And this is actually quite wonderful, because it means that we can write px greater than y, and we don't have to worry about whether we should in fact have written px greater than or equal to y, because the chance of equality is 0. And so you can write things like probability x greater than y is 1 minus probability x less than y, etc. Very useful.